Okay, for this video, I'll be going through graphing exercise 1. Okay, so we are presented with data full of a table full of data. So part A, they want us to identify any errors in the table. Okay, so the first error that I see is the heading. Okay, you shouldn't be using brackets. It's usually the physics quantity. Okay, slash its unit. So basically this should be L/M. Okay, similarly for this, it should be V/V. Okay, so this is the physics quantity followed by the units. Okay, so this is the first error. The second error I see is that for the length, right, imagine we are using a meter rule. So the meter rule's precision, is actually 0.001 meters. Okay, and because all of these are presented correctly to the correct precision, there's no error. But if we look at V, which is actually voltage, we see that it is not consistent. So 1.50, 1.80, 2.10. So if you have a chance to use a voltmeter, you'll see that actually it is half the smallest interval. So for this, we will take it that the error is 2.30, 2.60, and 2.80. Okay, so this is done. Now plot the graph of V against L. So the first physics quantity mentioned will be the Y. Okay, so it's Y versus X. Okay, and usually it is dependent variable versus independent variable. So your independent variable, okay, will be on the x-axis. The dependent variable will be the y-axis. Okay, so they want us to plot and then draw a best fit straight line. Okay, so we see that the L, it's the range is from 0.1 all the way to 0.6. Now when you're plotting a graph, there is no need to start from 0. No need to start from 0. Okay, so we see that for L, it is starting from 0.1 all the way to 0.6. V, it is from minimum of 1.5 to 2.80. Okay, so let us try to plot the graph now. Okay, so first of all, you need to label the axis. So this is L/M. Okay, so you don't need to put X or Y. Over here will be V/V. So in this case, I will be marking, usually the graph will be 4 marks. So I'll be marking for A, S, P, and L. So these are the 4 marking points. Axis, which is actually the Y versus X. This is the dependent variable, Y, versus independent variable, which is the X. Okay, so you need to label the axis with physics quantity / unit. Okay, like what we have shown over here. So if you have labeled them correctly, make sure that you do your y-axis correctly and your x-axis correctly, you get your 1 mark easy. The next point that we need to do is the scale. Okay, so remember L doesn't the graph doesn't need to start from 0, and our minimum value, it is 0.1. Okay, but if I were to start from 0, it is also okay. So this is let's see how many squares there are in the x-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 squares. So the graph paper may be different every time, so you need to count the number of squares. So So usually I'll count all the big squares. So there are actually 9 big squares in the x-axis. Okay, now we have to choose the scale such that the graph occupies more than 50%. So more than 50% in the x direction and more than 50% in the y direction. I'll be doing the x direction first. So if it's 50%, that means later on when I plot my points, the points must cover more than 5 squares, right? Because 9 big square, half of it is 4.5. So ideally, it should cover about 5 squares. So I can afford to let this x-axis be start from 0. And this is 0.100, 0.200, 0.3, 0.4, 0.5, 0.6, 0.7. And yeah, actually we will be at 0.6. Okay, so that is it for the x-axis, the scale for the x-axis. How about for the y-axis? It's starting from 1.5. So if you want, you can start from 1.5. So when you're choosing the scale, choose multiples of 2, 4, 2, 5, or 10. So if it's 1.5, now let's say if I start from 1.5, okay, and how many squares are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are actually 12 squares. Now, in order to cover more than 50% of the graph in the y direction, I need to cover more than 6 squares. Okay, so if I can do it like this, we start from 1.5, we have until 2.8. So we can do, if I do 1.6, 7, 8, 9, 10, 2, 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7. I wouldn't be able to cover my 2.8. Okay, so I got to think of a better scale. Let's see. Okay, I can do a 1.40, then 1.6, so I do multiples of 2, 1.6, 1.8, 2.0, 2.20, 2.40, 2.60, and 2.80. So how many squares do I cover? 1, 2, 3, 4, 5, 6, 7. Okay, yep. So I can actually cover 7 squares, right? And 7 out of 12 is actually more than 50%. Okay, so this is how you work out the scale. Then once you have worked out the scale, which actually you need some practice, but please do count the number of squares that the points occupy in both the x and y direction. Once you are done with the scale, then you can move on to doing the plotting of the points. Okay, so it's plotting of the points should be easy, because once you have identified that this is your x and this is your y, right? And usually I will put here my L is my x and this is my y, right? Okay, so it will not go wrong. So after that, I will do my plotting. Okay, I have plotted all the points. It's not difficult. Okay, and usually, how do I know which one will be on the x-axis? Usually, it's the one that we are able to determine. We are able to determine the equal intervals. Okay, yeah, because if you look at the y-axis data, right, it skipped from 1.5 to 1.8, then 2.1, and then go to 2.3. So it's not really equal interval. But for the x-axis, which is the independent variable, usually we can get them to be more or less very nice equal intervals. Okay, so now we have all these plotted points. Now you need to put your ruler and make sure that the line, best fit line, okay, the points are done, right? Now we need to make sure the best fit line passes the best fit line is as close to each point as possible. Now I can have a best fit line whereby I don't have any points on it. So let me show you how it looks like. Okay, because I'm doing on my laptop, so it's very difficult for me to draw my best fit line. So something like this. Of course, this is maybe an exaggeration or something. You see that I do not have, so this is a best fit line. I do not have any points actually on the line. Okay, and you will see that actually on the left hand side, I have 3 points. On the right hand side, I also have 3 points. Okay, or maybe I just put 1 point on the line. Okay, so I do have 1 point on the line, so I can actually turn my ruler, or I shift my ruler up and down, left and right, so that the line is as close to all the points as possible. But bearing in mind that, okay, just now on the left hand side we have 3 points. These are the 3 points, right? They are on the left hand side, and then I have these 2 points that are on the right hand side. Okay, so because one of the point is on the line, so 3 and 2 is okay. So maybe I show you what is not a best fit line. So I have 1 point, 2, 3, 4, 5, and 6, something like that. Okay, so this is quite common because students tend to like link up the first and the last point. They tend to link up the first and the last point, right? But if you think about it, if you just link up the first and the last point, then why is there a need to do the intermediate points, right? There's no need, ma. Okay, but because you're doing an experiment, you need 6 sets of data. Then your idea is to make the best fit line to be as close to all the points as possible. But why again is this not a best fit line? You see on the left hand side, there are actually 3 points on the left hand side. Yes, 1, 2, 3. Then there is 1 point on the right hand side. So this is not so good, right? So we are more skewed towards either the more biased towards the left or towards the right. Okay, depend on how you see it. Okay, so how do we draw a best fit line? We will again take your transparent ruler, rotate or shift up and down, left and right. Okay, it takes some kind of practice. So out of these 4 points, right, that we are marking for the graph, the axis should be easy, the points plotted should be easy. What you need to practice more is the scale and the line. Okay, so this covers the graph plotting, and usually it is 4 marks. Okay, so some questions they actually tell you that draw a best fit straight line. Now if it's a best fit straight line, we need 6 sets of data. Okay, and if you draw a straight line, you can calculate gradient. Okay, so how do I know it is a curve? Okay, how do I know it's a curve? So if it's a curve, right, they will usually ask you to calculate gradient at a certain point. Right? Because if it's a curve, right, then they say, oh, ask you to calculate the gradient at this certain point. What you need to do is you need to draw a tangent, right? You need to draw a tangent. So that's why whenever you receive the practical paper, the first thing that you need to do is to read through. Okay, don't just read first page and do as what you have read. You must first read through and understand what are you plotting. Okay, are you plotting what is your independent variable, what is your dependent variable, right? Then after that, when it comes to the gradient, is it a straight line, which is your rise over run, or is it a curve, right? If it's a curve, they will usually ask you to calculate the gradient at a certain point. Then that's where you need to draw your tangent. Okay, then if it's a curve, we will need 8 sets of data. Okay, a curve is rare in O-level, but it happened before. Okay, so now they want us to calculate the gradient of the line, showing clearly on your graph how you did it. This showing clearly on the graph means you need to draw your gradient triangle. Okay, and you need to indicate the coordinates. Okay, so this is show. So what do I mean? After you have drawn your best fit line, I'm just gonna draw my best fit line, something like that. Okay. Okay. Let's see if I can. Something like that. Okay. So this is your best fit line. Now, after you have drawn your best fit line, you don't need to care about your points already. You choose an appropriate point here. Okay, make sure that the gradient triangle is large enough. Then you do your gradient triangle, like what you do in math. Okay, so something like that. But what is more important is the gradient triangle must be large enough. Do not have your gradient triangle of this size. Okay, this is not good, because the percentage error will be very large. Okay, so I'm able to choose my gradient triangle as large as possible, preferably more than 50% of the line. Then what is more important is I need to label x comma y. That means I need to read, in this case is 0.700, and in this case is about 2.98, something like that. Okay, 2.98. Now, if it is unclear, because maybe your pencil is a bit blunt, or the markings on here is too dark, you can actually pull it out and then you write on the blank space beside. There will be blank spaces. Okay, so you need to do this, and you need to do another set of coordinates, your x comma y. Okay, then once you have your gradient coordinates, then you can do your y2 minus y1 over x2 minus x1. Okay, so now they say, hence or otherwise determine the value of v where your graph crosses the y-axis. So basically this is asking you for the y-intercept. The y-intercept, yeah. So why do they say hence or otherwise? Okay, so this depends on okay, I'm sure by now you have learned your graph, right? So is this the y-intercept? May not be. Okay, it depends on if the x-axis starts from 0. If it starts from 0, then this is the y-intercept, because the linear graph equation is y equals mx plus c. Now, in order to find my y-intercept, my x must be 0. Then my y will be the y-intercept. Okay, so in this case, this is the y-intercept, and you can read it off from here. But that is provided, very important, that your y scale starts from 0. Okay, but you know, we are required to draw the graph as large as possible to cover 50% of the graph paper in the x and y direction, right? So sometimes if, let's say, my x value starts from 5,000, next one is 6,000, example, something like that. Okay, so if this line actually touches the y-intercept over here, this is not the y-intercept, right? Because y-intercept only happens when x is 0. Okay, so I say this again. This is not the y-intercept because your x scale does not start from 0. Okay, so how do we then find the y-intercept? Simple, because they will always ask us to calculate the gradient first. They will always ask us to calculate the gradient first, right? So if you know your y equals mx plus c, you know your gradient, you can then actually use your gradient coordinates to sub in, and then you can use this to calculate for your y-intercept. Okay? Yup.